Okay, so here we go. Last time we were talking about center of mass, right? And remember the big idea of center of mass? And of course there are different ways to think about this. There's a sort of a physical intuition about, the balance point if you were going to try to get something to balance and not just kind of fall over immediately. But from a math point of view, I think the most natural way to think about this is that center of mass, this thing called center of mass, is the weighted average of position. And you'll notice that that's what this formula here represents. It's a weighted average. You can see the weights explicitly. The weights are the masses. I mean, that's pretty natural, right? So, and specifically that it's a weighted average of position. And again, you can see the position right in there, right? You can see it's those x's that we are taking a weighted average of with those weights. Okay, so mathematically very natural. Simple expression, and we talked about again sort of the basic physics of that. So this is an example with 2 points and 2 masses, and when it's only 2 of them, of course, there's a really simple formula for it. But when we're talking about the more general case, well, if you have a bunch of different masses, you would add those up, and if you have a continuum of masses, the continuous version of adding is integrals. And we saw that last time with looking at the average value of a function. You just replace a summation with an integral. So same idea down here. And here's our general formula for the center of mass of an object. Same thing that we've done in those previous examples. As we saw before, of course, here we're just literally adding up a bunch of pieces of mass. That gives us the total mass. That's a freebie. Okay. All right. Now, there is a sticky wicket on this, one little sort of eyebrow raiser, and that is, what on earth do we mean by an integral of a vector? We haven't done that before, right? That's pretty weird. Can you do that? Does that make sense? If you think about it, again, an integral really just adding or scalar multiplying and adding. And when you multiply a vector times a scalar, you do it one coordinate at a time. When you add vectors, you do it one coordinate at a time. So since that's all that's really happening deep down inside of this expression, it's done one coordinate at a time. And reminder that we have a formula for the coordinates of position. Those coordinates are x1 through xn. And so when you write out too much color coincidence. When you take this expression here, if you expand that by coordinates and recognize the integrals on one coordinate at a time, it's just this. Right? You can see those individual coordinates x1 through xn as these sort of coordinate integrams there. Okay. All right. So in practice, we do this one coordinate at a time. So example, suppose we have, I should definitely do that. If we have the upper half disk, as we see here, right? And we want to find the center of mass. Where is the center of mass of this thing? Well, we're going to follow our formula. We're going to do this one coordinate at a time. And here they are. Right, one coordinate at a time. The integral for the x coordinate of the center of mass has x in the integrand. Y coordinate, y in the integrand. Following the formula above. Okay. All right. Now, a couple of quickie things. What's with the area here instead of mass? Notice that the density was given as 1. Density is what you multiply times area to get mass. So if the density is 1, area is mass. Right? And so that's what's going on there. And then notice as well, even though I've written down 2 integrals that need to be computed, and notice furthermore, even though in the statement of the question there was no indication at all, not even a faint suggestion or a wink, one of these integrals is super easy. right? And you just got to be on the lookout for this kind of thing. This is how symmetry gets used in practice. It does not announce itself. Got to be on the lookout for it, right? So always head on a swivel looking for these opportunities. Now, what was the giveaway for me when I found myself looking at this integral for the first time, and the giveaway was the domain, and I see a glaring symmetry right there, and that makes me think, now that's only half of what I need, but maybe, fingers crossed, maybe, I don't know which integral it'll be, I've got two of them, but maybe one of these integrals, I might have a symmetry opportunity, right? And then you just check, and sure enough, one of them works. Yeah. Did you have a? No, I'm sorry. I thought I saw a hand. Thought I saw a hand. My bad. Okay. Yeah. So pretty sweet deal. Now I do encourage you, take a minute. Think about how you'd write down the details for that. Remember, if you're on the exam coming up later this week, right? If you want to cite symmetry, you got to give me those 5 details discussed last time. So. Great little practice problem. Think about how you would write down your explanation, including those 5 details. Okay. Now let's look at the other one. The other one, again, it's just a matter of kind of slicing it up. It's, I'm going to say, an unremarkable integral here. No particular challenge. Here are the 2 different ways that you could slice it up, noticing that my differentials here are in the opposite orders. And they both have square roots in them. We kind of knew that was going to happen, right? So what do you do? I mean, which one do you like better? I just want to point out there is something you can kind of eyeball on these to help you decide which one you think is going to be easier to evaluate. And I'm just kind of thinking about how is this going to play out. I'm looking at an integral of y dx. Basically, I'm going to be multiplying y times some square roots when I kind of work that out, and a substitution opportunity, and that's nice. Yeah. Okay. Now let's look at this one down here, and again, let's just try to, kind of peer down the road before we actually start walking down the road. First thing that's going to happen here, when I integrate y dy, I'm going to get y squared. I'll be plugging this square root into a square, and the square root disappears in a puff of smoke. No substitutions needed. It turns into a polynomial integral. That's better, right? So now, is it a big deal? Not really. Wouldn't I probably do this integral in polar coordinates anyway? I suppose, right? But I just kind of wanted to point out that when you find yourself looking at an integral, sometimes you can, at an eyeball glance, notice I didn't crank out any algebra here. Eyeball glance, I can help myself decide that I like this second one better. So, something to think about whenever you're looking at integrals. Okay, moving along. Reminder, today we're doing a bunch of applications to physics, engineering, and stuff like that. This being not a physics class, and tough choices and all that, I am actually going to leave out the discussion of the physics that goes into what we're about to see here. But here's the broad stroke. The big idea is that if I have a particle rotating around an axis, as I have here, right, then I can talk about the amount of distance that it's covered. I can talk about the angle that it's at, from some sort of starting position. I can talk about the radius of the rotation, various parameters I can write down. And I can also talk about the kinetic energy that it has moving around there. And energy is just a way of keeping track of, oh, golly, how do we define energy? Well, anyway, that's a physics thing, right? So again, not our goal here. So the problem comes up when we don't have just a point, but if we have some lumpy mass, some region where mass is distributed over the whole thing. How would I compute the amount of kinetic energy that this thing has as it rotates around? And the problem is that this little piece of mass right there only travels that far in one rotation, whereas this piece of mass over here travels a significantly greater distance in the same amount of time. This little piece of mass over here is rotating faster, literally moving at a faster speed. And so this problem, if I want to say what's the kinetic energy of this green blob, I don't know what to say for the velocity. It's not the same for all these pieces, right? So that is a nasty problem, and therefore this equation right here, in its attempt to apply to this scenario of computing kinetic energy, it just doesn't work. It doesn't make any sense. So the big idea for how to deal with this is to sort of change the question, sort of change everything angularly. And again, a certain amount of physics that we don't have time to talk about here. You can read it if you'd like. I think it's a pretty straight read. But anyway, the punchline is this formula for kinetic energy, given that we're looking at this particular rotational scenario, can be rewritten as this formula. And you notice they have a similar kind of looking structure. There's the 1/2, and then there's the thing, and then there's the something squared. Right? I mean, structurally kind of similar. Furthermore, if you look back through this development, this thing here is called angular speed, sometimes, unfortunately, called angular velocity. Whatever, it's fine. Okay, I'd prefer to call it angular speed, right? We said velocity is supposed to be a vector. Speed is a scalar. This is a scalar. I think angular speed makes more sense. But anyway, you'll notice that it is kind of analogous to linear speed. So, wow, what are the odds? These two formulas, they're computing kinetic energy. Structurally, they look the same, but one of these concepts is literally the angular analog of the linear thing that it's taking the place of. And so with that in mind, it makes sense to interpret this thing, which, by the way, is just this integral. That's just how the calculation developed. This thing here we should view as being, in some sense, kind of the angular equivalent of mass. If you're thinking about kinetic energy from the point of view of angular parameters of its motion instead of linear parameters of its motion, the thing that plays the role of mass is this weird expression right here, integral r squared dm. It turns out this is really important if you're doing any kind of physics that involves things rotating, which the universe is full of, right, heavily. If you're doing engineering and anything's rotating, which again, pretty common, right? Cars, car wheels, right? Pretty big deal. This is a fundamental natural physics concept, this idea of moment of inertia, they call it. There's the formula for it, and here's the way to think about it. Again, it's just an angular analog of mass. Okay, that's all we have time for on the physics. Now, I do want to talk about this formula a little bit more. We'll do a quick example. This formula right here, what can we say about the R there? And the temptation, the easy mistake to make is to look at that and think, oh yeah, I remember R, that's from like polar coordinates. Or oh, wait a minute, this is three-dimensional cylindrical coordinates, right? That's very tempting. If you look back up here at our setup, notice that's not what this is. R, as I have it set up here, is not distance to the z-axis. It's distance to whatever axis you're rotating around. And sometimes the thing that's rotating happens to be rotating around the z-axis. Sometimes, right? But very often it's not. So you have to kind of keep that in mind and apply this, interpretation to your circumstance. So in this scenario over here, again, our first scenario that I've got written down, we're rotating around the z-axis. Perfect. In that case, R, distance to our axis of rotation, is literally the distance to the z-axis. It's literally the cylindrical coordinate R that we're already familiar with. Okay. But sometimes, and usually I think is a fair statement, we're not going around the z-axis. We're rotating around some other random axis. Right? And what you've got to do in that case, in order to make sense out of this question, what is R? How do I compute r in this formula that I need to crank out? What you need to do is compute the distance from your arbitrary point xyz to that axis. You need a formula for distance to your axis of rotation. Now, in this case, because this axis just happens to have a simple representation, it's parallel to the x-axis in particular, the geometry works out really nicely and conveniently. You can draw this little triangle right there, and think about what these two legs are of that triangle, and without too much trouble, you can persuade yourself that this is your formula for r. In that particular case, every case is different though, right? So please don't try to memorize a menu of formulas to be applied in the finite number of scenarios that you may encounter. There's just too many, and to be honest, any finite list is doomed to be incomplete. Right? So better to always look at your geometry. So a couple of extra scenarios here. There's what distance to the axis looks like if your axis is the y-axis. Note in this case our area happened to be a two-dimensional area in the xy plane. And so the formula is actually significantly simpler. Peculiarity of the circumstance. Okay? And then likewise another example over here, and again you can think through all these details. Okay. So the point is always look at your scenario, interpret accordingly. All right, so an example. We have here a region, solid region, right? Mass is distributed across that region according to that formula. Notice the density is not constant. And we've been asked to compute the moment of inertia. Now again, why would we be interested in the moment of inertia? Because if I want to think of this as being something that's rotating, in particular in this case, rotating around the x-axis, and if I might be interested in kinetic energy or something like that, I need to know what should I think of as playing the role of mass, and that's what moment of inertia is. So computing along, don't forget moment of inertia is this handy-dandy little formula. By the way, always, in all circumstances, it's always integral r squared dm. If it's a two-dimensional, it's a double integral. If it's a three-dimensional solid, it's a triple integral. Right? It's always appropriate to the circumstance, but it's always whatever the integral is over that mass. Okay. Whoops. Okay, in this circumstance, what can I say about this r here? What is r? Well, we're rotating, it says right here, around the x-axis. There's the x-axis. Right? Looking at our region. Looking at an arbitrary point in my region. What is that distance from my arbitrary point to my axis of rotation? I have myself now a little picture of what my r is, and again, casual glance. Just study the geometry of the picture you've created, and well, conveniently, that distance there, it's just y. That's all it is. So r is just y. Everybody happy? All right. Okay, one other little thing you may recall, and I'll go ahead and point it out while we're here. The dm, remember that represents a little piece of mass. Mass is density times size. This is two-dimensional, so density is mass per unit area. Size is the area. So density times area, and you'll notice that that's what we actually have here as well, and in particular, this density we were given, that density just goes right there, and of course, obviously, dA is dx dy. Everything else is plug and chug, and that's all I'm going to say about section 5.6. Again, it's just various applications to certain physical scenarios. Okay, how are we doing? Is everybody on board? Okay. All right. Yeah, okay, on to, let's see here, I need to do this and then move on to this Page of notes here. Stretch it back out. Okay, on to chapter 6. So this is where the course starts to venture into the really exciting part of the material. I think this is the most beautiful part of the course. It does take us a while to kind of work our way up to that. But just to let you know what a kind of a sort of oversimplified description of where we're going with all this is we're going to find that there are various generalizations of the idea of the fundamental theorem of calculus. The fundamental theorem of calculus is just that's just the real line, just an interval, kind of the simplest possible case. And we're going to sort of extend that and generalize it up to some multivariable applications. Actually really exciting stuff and beautiful mathematics. Things kind of fit together in sort of mysterious ways. Lovely stuff. But we do have to work our way up there. We're going to start off defining something called a scalar line integral. As you can see here, we will eventually talk about something called a vector line integral. That's a different critter. They have certain things in common, thus the shared terminology of line integral. But vector line integral is a significantly different thing. For the moment, scalar line integrals. Okay, so here's the question. Notice every domain we've seen so far, whether we were doing double integrals, single variable integrals, triple integrals, integrals in different coordinate systems, which is really just a computational tool, right? It's not really a fundamentally different kind of integral. It's just a trick, basically. But all of our domains have had the same dimension as the world that they live in. When you're doing a double integral, it's always a two-dimensional region that lives in a two-dimensional world. When you're doing a triple integral, it's always a three-dimensional solid domain that lives in a three-dimensional world. Okay. So we're going to entertain now the question of what if that doesn't happen? What if our domain is dimensionally smaller than the world that it lives in? And this happens, right? So we can talk, for example, about a curve that lives in space, or easier, a curve that lives in the xy plane. Right? So, for example, suppose I had a domain that was, let's say, kind of like this. Now, what do I mean by that? What do I mean by this is my domain? When I chop it up, add it up. There's some quantity. Again, let's not get worried about what the quantity is, but there's some stuff that I want to view as being accumulating over not a two-dimensional region, but over a curve in the plane. And so, weird question, if I wanted to do a chop it up, add it up on this domain, is that it's in two dimensions. Should I use a double integral? You can't use a double integral. Double integrals have a dA at the end. They're talking about size as being area. This is a curve. It doesn't have any area. Okay, well, can I do single variable calculus? Can I just call this a single variable integral dx? And notice, no, look at the size. It's not represented by how much x changes. It's represented by a length. It's going partly in the x direction, partly in the y direction. So it's not a single variable integral as we've currently understood it. It's not a double integral. What do we do? And the answer is you create a new kind of Riemann sum. This is really not that spooky. Ultimately, it's just, look, chop it up, add it up. Right? Appropriate to your circumstance. So I'm going to add over all these little pieces by looking at one little piece at a time. Let's look at this little piece right here. On that little piece, whatever it is that I'm interested in adding up, we'll just look at one piece at a time. Now, my favorite, metaphor, right, example quantity to talk about is mass. Very relatable, very sort of easy to talk about. And okay, well, how much mass is there in that little piece? Well, I would take mass per unit length and multiply by length. Maybe there's ants crawling all over this thing, and I want to know the total number of ants. Okay, fine. Then on this little piece, you'd multiply ants per unit length times length, right? And that would give you ants, and then you add up all the ant counts that you have along the whole curve. Now, don't worry about the computation. We'll get to how to compute this momentarily, right? But just from a chop it up, add it up standpoint, that's really all that's going on here. Notice the quantity could be anything. It's not the point. This could be what, I don't know, any sort of a quantity where the whole is the sum of the parts. Could be mass, could be ants, could be work, or could be maybe some application in economics. I don't know enough about economics to know what that might look like, but you never know, right? Anything where the whole is the sum of the parts. That quantity then, I need to talk about how much of it there is per unit length, and that's what my integrand is. It's always quantity per unit length that I multiply by length. So the integrand, always a density of some sort. Density appropriate to whatever your quantity is that you're accumulating. Now it's just a matter of writing down some notation, and this is just notation to kind of just a convenient shorthand so I don't have to write down clunky Riemann summation notation all the time. And you could probably see this coming, but we're going to use an integral symbol to represent limit of sum, as we do for every other kind of integral. Right? Big surprise, we're going to represent delta S with ds. Not a shocker, I hope, right? So again, pretty standard. So this notation right here is actually pretty straightforward, and I think pretty believable. Pretty expectable, you might say. How are we doing? Is everybody on board with me? Is everybody happy? Okay. All right. Again, this is an abstraction. This is a hypothetically, wouldn't it be nice if I could chop it up into little pieces? This integral here that I've just defined, we have no earthly clue at the moment how to actually compute it. All this is a shorthand for a strategy where we're basically saying, let's chop it up into little pieces. Maybe that'll help. And we still haven't really done anything. Okay. All right. So I'm going to say that these are undesirable domains. And what I mean by an undesirable domain should hopefully be obvious. I don't know what to do with it. That's undesirable. Right? I want to point out this is not the first time we've seen undesirable domains that we're unhappy about. Change of variables. Right? Change of variable. That was a different kind of undesirable. What did I not like about domains when I was doing change of variables? I don't like the corners. Right? I don't like that the curves that describe the boundaries might be ugly or something like that. Right? So undesirable in different ways. These domains here are undesirable because they're the wrong dimension, for crying out loud. Right? And that's really kind of killing us. Okay. All right. So, but that said, they are undesirable, and we're going to do what we've done before. When you have an undesirable domain, again, here's our undesirable domain. What we do is we view it as being an image, right? Specifically, this undesirable domain is the image of this this green interval back here, and then we're going to do a pullback, right? And the integral that I've got defined over here, that I don't know how to do that, I'm going to pull it back, realize it as an integral defined A to B on the real number line here, right? World's easiest domain for any integral, just a single variable integral over an interval. Same basic idea. Is everybody willing to buy it strategically? Again, details to follow. All right. Okay. So, a couple of details. really not that big a deal here. It's going to work out very conveniently. Let's see here. The whole point to position here, x, is that it is the image of t. It is a function of time. Right? When I parameterize that curve, position is a function of time. Right? That's literally just plugging in. Let's see, the other thing, now here's where we're going to have to actually do some thinking, looking at this size, right, ds, representing how big that little piece of the curve is. Well, how big is it? Well, it's a length, and I'm interested in how length relates to a little piece over here, which is a little piece of time. And what is the relationship between distance and time? Speed, right? So this ds that we're looking at, the way I'm going to write that in terms of time, dt, is to realize that the stretching factor, how much bigger is the output than the input, however you want to say it, is just speed. Magnitude of your velocity vector. Is that cool? Any questions? Is everybody happy? All right. So sure enough, we've done our pullback. Let's see here. Right? We turned the integral that we don't like into now an integral that's over here on the t-axis. This is this Math219 Calc 1 integral, right? Integral from a to b, dt. Everything in here is a scalar. Plug and chug. Okay, let's do something. Oh, yeah, real quick before I go on to actually doing one, just a concern you may be worried about. You could be worried about, arguably should be worried about. This parameterization that I picked here, how I parameterize that curve. Recall, there's a bunch of different ways to parameterize a curve. Right, countless different ways to parameterize a curve. What if I parameterize the curve one way and then someone else parameterizes the curve with a different parameterization? They're going to get a different integral. Which one's right? Is there a particular special parameterization maybe that we ought to use? Certainly something we might ought to be worried about. What if my parameterization gives a different answer than someone else's parameterization? Which one is right? So here's the good news, and that is it doesn't matter. This expression here is independent of the parameterization. Parameterize however you want. Knock yourself out. It's all good. You're going to get the same answer either way. So make your life easy. Use whatever is the most convenient parameterization for the circumstance. And you don't have to worry about it. Okay. Okay, so example. Here we go. We've got a scenario here where we have an irregular wire, right? Kind of like the picture I had drawn. We're parameterizing that path that it follows right here. Parameterization given. Now again, in the real world, is the parameterization given? Maybe, maybe not. Sometimes, I suppose. If it's not, again, we've got techniques for how to parameterize things. Right? My favorite being the graph parameterization. Very handy in a lot of circumstances. But anyway, this case, just to get the ball rolling, and assume the parameterization is given. And this wire is not of a constant density. The density depends on location in this way here. So we've got this lumpy kind of a wire, and I want to compute the total mass. Well, wait a minute. I actually want to compute several things. I want to compute the mass, but I also want to compute the center of mass. I also want to compute the moment of inertia around the x-axis. I want to compute a bunch of different things here. All right. Just for dramatic effect, I'm going to compute them all at the same time, right? Just because these computations, as it turns out, have a lot in common. So in particular, how How am I going to compute mass? The whole is the sum of the parts. It's an accumulating quantity. And so I get an easy scalar line integral to represent mass. How am I going to compute the, we're going to start with the x coordinate of the center of mass. Well, again, we have that written as an integral. Weirdly, the whole is the sum of the parts. Kind of strange. Again, that can be rewritten as a scalar line integral. Okay. Now, it's tempting to look at these two integrals and say that, well, they're pretty different, right? But these two integrals, let's see here, I'll do it like this. This integral and this integral, they have a lot in common. In particular, they're integrals computed over the same curve. Same curve that we can parameterize with the same parameterization, which has, as I move along the curve, the same velocity, because I'm using the same parameterization, because I'm on the same curve, right? And if it has the same velocity, then it also has the same speed, right? So that's why I like doing these calculations in parallel. So much of the setup of these scalar line integrals is exactly the same, because we're computing different things, but we're computing them on the same curve, and that makes a tremendous convenience. Okay. All right, so now it's all over but the details. Let's walk through a couple of these details just so we can say we did. Let's see, here we go. Let's see here, what is ds? Well, ds is speed times dt, same in both integrals. Let's see here, what is density? Oh, okay, well, density was given. Density is x plus y, same in both integrals. Right. What are the bounds for our integral? My bounds, keep in mind the bounds are just the bounds on the pullback variable. So where does t start and end? Well, again, given 0 to 1. So both of these integrals, 0 to 1. The only difference in these integrals is that this one over here has an extra factor in it, this x right there, because, well, we're computing a different thing. Obviously, it's a different integral. There's going to be some difference. There it is. It's just what that x is. Now, last remaining question, how do I actually turn all this in terms of t? And just keep in mind that all this stuff is already given in terms of t, and I have computed in terms of t. So, for example, what do I do with, let's see, this x prime? Well, I already computed it. There's x prime as a function of t, same in both integrals. What is x? Ooh, convenient, given. Right? Don't forget, what you're pulling back through is the formula for your output variables as functions of your input variables. That's how you just plug that in. That's how you do the pullback. So x is t in both of these integrals. How are we doing? Is everybody following? Everybody happy? Likewise, y, of course. Let's see here. Yeah, there's y. So y is t squared in both of these integrals. And now plug and chug. Two completely pulled back integrals. That one computes mass. This one computes the x coordinate of the center of mass. And by the way, totally analogously, you can compute the moment of inertia, and you can compute the y coordinate of the center of mass. Exact same arguments. I'm going to let you all read those details for yourselves. Is everybody happy? Okay. All right. Moving along, another example here. This one's a little bit less physicsy. But let's suppose that you have a fence, and the fence has a non-constant height. The height of the fence is it's higher over on what you might call sort of the eastern side of your property, and it's lower on the western side of your property. Now, why would you do such a thing? I don't know. it's not important to the example. But I can imagine, depending on where your house is located, maybe you need privacy from that nosy neighbor on your east side, right? Possibly. Maybe you've got a vegetable garden somewhere, you want it to get more sun, whatever. Okay. So we want to compute the area of the fence, and why on earth would we want to compute the area of the fence? Maybe I want to paint it, right? And the whoever it is that I hired to paint the fence is going to have to buy the paint, the stain, whatever, right? And or maybe he's going to make me buy it, and we're trying to figure out how much this is going to cost. Okay. So here we go. Here's the base of our fence is moving along the unit circle like that, which fully stretched out. It's kind of like this. But let's just look at one little piece of that fence, and let's see here. Here is a picket, let's call it. All right, that's got a certain amount of area, and the very first observation I'm going to make is that the total area is the sum of the areas of the pickets. I think that's a pretty easy pitch. Does everybody buy it? Okay. Whole is the sum of the parts. Right? This is an accumulating quantity, however you want to say it. Okay, what can we say about that area? And area is conveniently height times width. Now, the width here is just ds. It represents the length, moving along a little piece of our domain, a little piece ds, which you see there. And, of course, that's being multiplied by height, which you see right there, right? So height times width gives me area. Everybody all right? Okay. All right, so we have ourselves a scalar line integral. We have a process for computing scalar line integrals. Let's see, what is our process? Quick reminder. Our process for computing a scalar line integral is step one, to parameterize that curve. In other words, view it as being an image of a nice pullback domain. Yeah, go ahead.
Sorry, I had a question actually about the setup.
Oh, yeah. Mm-hmm.
DS is tilted, so as you go farther to the right, it's going to get more and more steep, so you're going to have a larger DS.
Yeah, that's right. So DS right here is dramatically not DX, right? And yet DS over here is not that different from DX. So yeah, that's right. It is going to be different in different places. The whole idea is that I can see how these are. Don't think in terms of coordinates. Think in terms of how fast am I moving as I'm moving along that piece of curve, right? And that it doesn't matter what direction you're going. Length is speed times time, right? And so you'll notice that that's the way that we have this broken down here. I'm not thinking of ds in terms of my dx differential or dy differential. Thinking about that length in terms of dx and dy is weird. Don't do that. Think about it in terms of dt. Does that make sense? Sure. Yeah. Everybody happy? Okay. All right. Okay. So how do we do this? Well, we need to parameterize our curve. Our curve, recall, is this unit circle. I have a favorite parameterization of the unit circle. Right. Our old friend. Compute the velocity, compute the speed, a couple of derivatives, magnitude, right? Easy stuff there. Conveniently, you will rarely get this lucky, right? But my speed is 1. Isn't that nice? Don't take that for granted, right? Most of the time that won't be the case. Anyway, that said, here is my scalar line integral, and keep in mind, step 1, I've got to figure out how to rewrite ds. There's my PAT formula for ds. Distance equals speed times time. This height function, I'm losing track of my colors. This height function is given. It was x plus 2 over 5. That's just given in the statement of the question. Right there. mostly over. One last little detail I do have to fill in, and that is that my speed, whoops, wrong color. Let's see here, green. My speed is 1. Yeah, and then of course, now wait a second, what's x? I got to figure out how to plug in for that x right there. What do I do with that x? Right, the parameterization tells me what my x is. My x, cosine t. So just plug it in from the parameterization. Everybody all right? And so now again, single variable calculus. And okay, so it's a little annoying sometimes, but integrals don't go away. So make sure that you're good with computing this. All right. Okay, so there's lots of examples of this kind of thing where you have some sort of a scalar quantity that accumulates over your curve, where the curve is in the plane or in space, whatever the circumstance may be. Now here is another, I'm going to say an example. I'm going to say we're going to try to apply our existing idea to a new circumstance, and we're going to have to see what happens, and something weird is going to happen here, a little unexpectedly. Okay, so flashback to chapter 1. We talked about this formula right here. Work is force times distance. Wait, that's kind of a high school point of view. The high school then has to quibble and say, well, it's not really the force. It's the component of the force in the direction you're actually going. I don't really care about force perpendicular to the direction you're going. And so, a little bit of trig gets involved, right? And what we saw in chapter 1 is that you can resolve that very nicely just by treating force as being a vector, as you should. It is a vector. It does have a direction. And likewise, treating distance as displacement, again, as you should. Anytime I walk a certain distance, I'm always walking that certain distance in a direction. Right? It is intrinsically, naturally a vector. So what we saw in chapter 1 is that if you just treat these things as vectors, as they are, as you should, then the formula for work turns out to be really nice. It's a dot product. And that resolves all this issue about components and stuff like that. We no longer have to worry about it. Okay, that said, there is still a weakness in this formula. This assumes that F is constant over your whole displacement. Sadly, not true in general. It also assumes that you're moving along a straight line path, which again, tragically, also not true in general. So what we're going to try to deal with here is how to compute work if I can't use this formula because, for example, I'm driving along this windy mountain road here, or walking along this windy mountain trail, whatever the case may be. If I want to compute the grand total amount of work, notice the force is dramatically non-constant, right? I mean, at points around in here, my force vector is about like that. But at points over here, my force vector is about like that. Very much not constant. Right? And of course, pretty obviously, this path is very clearly not straight. So what are we going to do? Now, the answer to most questions in this class, what are we going to do? This being a calculus class, right? I mean, we're using integrals. That's what we do. We use an integral. We chop it up into little pieces, and then we add up on those little pieces. All integrals have this in common: chopping it up, adding it up later. Right? So here we go. Fine. We're going to look at little bitty pieces here. Let's look at this little bitty piece right there. And on that little piece is approximately straight. Not exactly. But, I mean, in the limit, as I chop more and more finely, that gets smaller and smaller and straighter and straighter. Right? Furthermore, the vector field, it's not exactly constant, but it's approximately constant in the sense that what the vector field is looking like there and what the vector field is looking like just a few inches over, probably not that different. Again, because it's getting smaller and smaller. So we just chop it up into little pieces and then add up on those pieces. Is that cool? All right. Okay. There is one difference that I do have to worry about. Now, very importantly here, the question says to compute work. Notice that I'm moving along this path. So I'm going from this blue starting point to this red ending point. And if you've ever walked a mountain path, you notice there's a very different amount of work involved going uphill versus going downhill, right? So when we ask, how much work does it take, there's something about the question that is intrinsically going a certain direction, right? The fact that we are going this way along the curve is key, right? How much work does it take to climb the mountain? Okay, this is a lot of work. How much work does it take to come down the mountain? Give me a pair of roller skates, right? And put a cushion at the end. It takes almost no work at all, right? I got to guide myself, right? Yes?
When you're making the bounds, how's that going to look? Is that going from
Oh, yeah, details to, you're asking natural questions, but that we are going to get to that, but we have to kind of think about the sort of the big picture first. But yeah, we'll totally get to that. Not today, obviously. Oh, I come to think of it, I'm out of time today. Really quick, let me just point out that this is called an orientation, and we'll pick up from there next time. Y'all have a good one. See you later.